Hello, welcome back to your physics teacher, and in today's lesson we're looking at section 1.2 from the Nelson textbook. I selected a couple of questions to answer here, so to help you out with your homework. Feel free to look at the scroll bar below and select the question that you had the most trouble with, that way you can get the help that you need. Starting from the first question though, we have: upon leaving the starting gate, a racehorse accelerates at a constant 4.1 meters per second squared forward for 5.2 seconds. Determine the horse's A, displacement, and B, final velocity. As a quick reminder from grade 11, we should try to follow the steps that we highlighted before, which is first to visualize the problem. Second, you want to draw your coordinate system. Then 3, 4, 5, 6, you're going to be setting up your displacement, velocity, acceleration vectors along with the time interval. Finally, you look at the equations of motion, you choose the best ones, and then you solve the question. Now, let's try to visualize the problem then as the first step. So here we have a racehorse, and they're giving us that this racehorse is leaving the starting gate. Since it is a race, then we can start to assume a couple of things about the motion, that the horse is going to start from rest. So here we could have that the initial velocity is going to be 0. And like I mentioned before, after we visualize the problem, we want to set up the coordinate system. In this case, the best place to usually place the coordinate system is right where the object's motion begins. So we're going to set it up right where the horse begins. This means that anything to the right, we're going to take it as positive, and anything up is going to be positive for the vector quantities. The first vector that we want to take a look at is going to be our displacement vector. So here we are assuming that the motion is in one dimension and the horse moves to the right. So our displacement vector is only horizontally and it points to the right, which is why we take it as positive, and this is our unknown. That's what part A was asking us. What is the displacement? And secondly, we want to be looking at our velocity vector. So like I mentioned before, we are assuming that it starts from rest, and after some time the final velocity we don't actually know, but the object is moving to the right, so we know that it's going to be pointing to the right, because velocity points in the direction of motion. And during this whole displacement, the acceleration is forward, which we're assuming that in this case is to the right. So our acceleration is 4.1 meters per second square in the forward direction. And this whole displacement takes place in some time interval, delta t, which is 5.2 seconds in this question. Now we have all the main steps for the setting up this problem. Then, since it is a kinematics one, we're going to be using the big 5 kinematic equations of motion. But usually I only use 3 of them, so I'm going to write them down, the 3 most important ones. Alright, so now that we have the equation of motion, then we look at what they were asking us. So we're looking for displacement. So our target is going to be either from equation 1 or equation 3. But we don't have the final velocity, so equation 3 wouldn't be the best choice in this case because we don't have the final velocity. But notice that equation 1, we have the initial velocity, the acceleration, and the time interval. So this equation is probably the one that we're going to have to use. So we're going to rewrite it, and then we're going to substitute in what we're given while considering the direction, if it's positive or negative. Our displacement is to the right, so we can take this to be a positive number. Our initial velocity was 0 since the horse started from race at the starting gate. Our acceleration points to the right, so we can take it to be a positive quantity. So let's rewrite this. Delta D equals to 1/2 a delta t squared. And plugging in the numbers that we know, we get that our displacement is approximately 55 meters. Now it is a vector quantity, so this means that we should write our final statement as a vector, so it's going to be 55 meters, and we assume that to the right was the forward direction, so we have to give it the forward direction. That would be part A. And what was part B asking us to find? Part B was asking us to find the final velocity. So in this case, we are going to be looking at either equation 2 or 3. We have the initial velocities, we have acceleration, we have the change in time and displacement. So it turns out you could use either equation 2 or 3. Equation 2 will be easier to use in this case because there's no need to be squaring. A lot of the time students make a mistake with squaring, so make sure you choose equation 2. It is going to be easier to handle mathematically. So let's first rewrite it, put in what we're given before we substitute in the values. Our final velocity is positive, and it's because it points to the right. The horse started from rest, and our acceleration pointed to the right, so we take it as positive. Simplifying to V final equals to A delta T. Substituting in our values, we get approximately that the final velocity is 21 meters per second. And again, this is a vector quantity, so let's write down our final statement as a vector. So it will be 21 meters per second. And again, velocity points in the direction of motion, which in this case, it's going to be forward direction. All right, so once again, our problem solving steps is going to be visualizing, coordinate system, displacement vector, velocity vectors, acceleration vector. Consider your time intervals, the equations of motion, and then you try to select the best one while still considering when you put it into the equation whether it's going to be positive or negative depending on the direction that the vector points towards. So let's look at a couple more examples so that way you get reacquainted with kinematics from grade 11. Looking at question number 2 now, we have an electron traveling at 7.72 times 10 to the power 6 meters per second east enters a force field that reduces its velocity to 2.46 times 10 to the power 6 meters per second east. The acceleration is constant. The displacement during the acceleration is 0.478 meters east. They want us to determine the electron's acceleration and to determine the time interval over which the acceleration occurs. Once again, we're going to try to use the same method of problem solving that we've been using before, which is to first visualize the problem, then we're going to set up a coordinate system and look at all the vectors along the time interval before we get into selecting the equations. Now, what is a bit strange about physics is that the way we visualize electrons, we just write E minus, and usually we make them around a blue circle, like a blue ball. So that's an electron. Now this electron, let's set up a coordinate system for it. And whenever you're trying to set up the coordinate system, the best one is to usually set up the origin right where the motion of the object begins. And by convention, we're going to take to the right to be positive and up to be positive. And because they did tell us that the displacement was east, that's why I drew more space along towards the right. They tell us that the displacement is east, so it points to the right. Delta D equals to 0.478 meters east. Then we want to look at velocity vectors. And this electron's already traveling with some initial speed. So here we could label this V initial as 7.72 times 10 to the power 6 meters per second east. So in other words, we're going to draw the vector pointing to the right. Now it enters some force field not sure if that's the right way to say it, but it enters some region of space where it begins to slow down, which suggests that the acceleration has to be to the left. That's the only way we can get this electron to slow down. So our acceleration vector is to the left, and this value we actually don't know. So it's going to be our unknown. At the end of this displacement, they tell us that the final velocity has slowed down to 2.46 times 10 to the power 6 meters per second east. So we should represent the velocity vector smaller than the initial one. All of this takes place during some time interval, delta t, which we don't actually know. And this is how we try to set up kinematics problems. So again, visualize coordinate system, displacement, velocity, acceleration, then time intervals. And then you go ahead and write the big 5 kinematic equations of motion, or in most cases you only ever need 3, which is why I only write 3 of them. Alright, so part A was asking us to find the acceleration, and part B was asking us to find the time interval. Let's look at our equations, and all 3 of them have acceleration, so all of them are pretty good candidates to use. But so far we don't have the time interval. So that's where equation 3 comes into play, because I used the clock to remind that time has stood still, but it really hasn't. It's just to remind that this equation does not depend on time. So that's the one we're going to have to end up using. So equation 3, because we have the displacement and the velocities. So we're going to rewrite equation 3 and then substitute in what we're given while considering the direction for positive or negative when we're subbing in the values. In this case, our displacement is pointing east, so we could take it to be a positive value, so it could just be delta d. Our acceleration was pointing to the left, so we could write negative a. And for the velocity, since we are squaring them, it doesn't matter if it's positive or negative, because when you square them, it will get rid of the sign and make them positive. So now let's try to isolate for acceleration, because that's going to be our unknown. Oh, I got a bit ahead of myself. Let's first rewrite this, then simplify. Okay, to simplify and isolate for A, we want to divide both sides by 2 delta D negative. So this will leave us that acceleration equals to V final square minus V initial square divided by negative 2 delta D. At this point, once we substitute in the values that we were given, you should get that the acceleration is 5.6 times 10 to the power 13 meters per second square. But this was the magnitude. Since acceleration is a vector quantity, we should rewrite this as a vector. 5.6 times 10 to the power 13 meters per second square, pointing to the left, which we can say west. And part B is asking us to find the time interval. Now we look at the equations of motion, and since now we found the acceleration, we can use either equation 1 or 2, and it's much easier to use equation 2. It will make the algebra less demanding, so we can use equation 2 now. Our final velocity points to the right, so it's V final. Our initial velocity points to the right, so it's V initial. Our acceleration points to the left, so it will be negative a. Simplifying to V final equals to V initial minus a delta t. Now our goal is to solve for the time interval, so we're going to have to do some algebra. So we're going to move that V initial to the other side by subtracting both sides by V initial. And to isolate for the change in time, now we're going to divide both sides of the equation by negative a. So this gives us that the time interval equals to v final minus v initial divided by negative a. Putting in your values, you should get approximately 9.39 times 10 to the power of negative 8 seconds. Alright, so let's look at question number 6 now. And question number 6 reads, you throw a ball straight up into the air at 18 meters per second from a height of 32 meters above the ground. And they want us to calculate the time the ball takes to hit the ground. We'll take care of the rest after. So here, once again, you throw a ball straight up into the air at 18 meters per second from a height of 32 meters above the ground. So in our problem solving method, the first step is we want to try to visualize. So let's draw a quick picture. So in this case, we have a person throws a ball straight up into the air, and then it falls back down, and when it falls back down, it hits the ground. We want to set up the coordinate system, and as I mentioned before, the best place to usually put it is right where the object's motion begins. So in this case, right where the object begins to be thrown. With this convention, anything to the right, we take it as positive, and anything up will be positive. Once you do this, then you can talk about your displacement. Now, displacement is the change in position. So from the hand to the ground, the displacement will be pointing downwards. So the displacement that it took to hit the bottom. But this is the same height that was given to us because the object was thrown from a height of 32 meters. So this will be 32 meters. But the part that you need to watch out for is that the direction is actually downwards. So you put down. Or another way to represent it, you could write negative 32 meters. Once you have the displacement, the next thing we want to look at is the velocity vectors. So at the moment that it's thrown, it is thrown with some initial velocity, and it is 18 meters per second up. Now, since they want us to calculate the time that the ball takes to hit the ground, the final moment will be just before it hits the ground, and this we actually don't have the final velocity, so it's an unknown. And during this whole motion, because the object is thrown up into the air, and we are assuming that there's no air resistance, but we do know that we are on the planet Earth, so the acceleration that is experienced is going to be motion under gravity. In other words, the acceleration is due to gravity, so A equals to G, which we can approximate as negative 9.8 meters per second square. And this whole motion of going up and down to hitting the ground took place over some time interval, which we don't know, and that is what we're looking for in part A, so the time that it takes to go up and down. And now let's write down our three main equations of motion, which will help us to filter out which we're going to need to use to answer part A. So in this case, we are interested in the time, so that means that we're looking at either equation 1 or 2. But we don't actually have the final velocity, so equation 2 wouldn't be a really good candidate. This means that we narrow it down very quickly to the main equation, equation number 1. So what we're going to do, we're going to rewrite this equation, and then we're going to substitute in the information that we are given. Now, the things that we're given is that the displacement from the hand to the ground is the total height above the ground, which was 32 meters, but since the direction is downwards, we have to put in negative 32. And the initial velocity, since it's pointing up, we take it as a positive value, so 18. The change in time, that's what we're looking for, 1/2. And the acceleration, because it is the motion under gravity, which is pointing downwards, so we're going to replace it by negative 9.8 delta t squared. Now let's try to simplify this a bit. What we're going to do, we're going to move the 32 to the other side. Negative 32, sorry. Now, since we were looking for the time, that's why I try to put it in yellow to highlight your attention. But I also want to do something else to highlight your attention, which in order to solve for the time, this equation appears to be quadratic in time. So what that means is you're going to have to recall from grade 10 math the quadratic formula. So you're going to think of this as being quadratic in time. And what this means that in order to solve this equation, we're going to have to use the quadratic formula. But for our case, x is the change in time. So let's replace this, delta t. Our b is actually 18. Our a is negative 1/2 times 9.8. And our c value is 32. So this looks really complicated, and then we are going to get two values. So we get that either the change in time can be 4.984 or negative 1.310. So this means that we're going to take the positive answer because we couldn't have the negative time. And we're going to approximate it to be about 5 seconds to make our life easier. So in order for the ball to hit the ground from the hand, from the point that it was released, it's going to take about 5 seconds. Part B asks us to calculate the velocity of the ball when it hits the ground. So in order to solve this from the kinematic equations that we have, we could use either equation 2 or equation 3. And it turns out that we could use either one because we have the displacement, the acceleration, and the change in time now, along with the initial velocity. So take your pick. I'm going to pick the easier one to work with, which is going to be equation 2. So let's rewrite this equation and then substitute in what we're given in order to simplify it. So in this case, again, our acceleration and motion under gravity is going to be given by negative 9.8. Our initial velocity was pointing up, so we take it as positive 18. Our final velocity is unknown, so that's what we're trying to find. So we don't know that direction. Well, we do know, but let's just leave it as an unknown. That's why I'm going to leave it as a vector quantity on the left side. So v final equals to 18 minus 9.8 delta t. And we already calculated the time that it takes to hit the ground from the hand, which was 5 seconds. So let's substitute that in. And if we are correct, we should get a negative value. So let's check. Yes, we got negative 31 meters per second, which can be rewritten as v final is 31 meters per second down. Part C in this question is asking us to calculate the maximum height of the ball. So now we're looking for another displacement. So from our diagram, delta D top. So the displacement from the hand to the very top, we call it delta D top. But they're asking us to calculate the maximum height of the ball. So here we're going to have to consider from the ground to the maximum height. So we're going to have to add up our delta D bottom and our delta D top. The maximum height from the ground, we're going to call it capital letter H for height. And this maximum height is just going to be the distance from the ground to the hand, which we call delta D bottom. And from the hand to the very top, delta D top. So notice that these are scalar values. There are no vectors to them. So we're taking the scalar portion of it because we're measuring the length. The distance from the bottom to the hand they gave to us is 32 meters. So the thing that we're looking for now is the distance from the hand to the maximum height, delta D top. Let's go back to our diagram and try to figure this out. Now, whenever you throw objects up into the air, once the object reaches the maximum height, because as the object is rising, it is slowing down because the acceleration points down, velocity up, so the objects are slowing down. Once it reaches the maximum height, we say that the object is momentarily at rest. In other words, the velocity at the top is going to be 0. And this is because, as we just finished saying, so we're going to be able to use our equations of motion, knowing that at the very top, the object is momentarily at rest. So velocity at the top will be 0. So now things are a bit different. We're looking for displacement. So this means either equation 1 or 3. And we don't know the time that it takes to go to the very top. So we won't be able to use equation 1. But equation 3, we know the acceleration, initial velocity. And since we just said the final velocity is 0 at the top, we can use the third equation. Let's rewrite it and simplify. The final velocity is actually the velocity at the top, which we said is 0 because that's when it is momentarily at rest. Our initial velocity is up, so it's positive 18. Our acceleration is due to gravity pointing down, so negative 9.8. And our displacement, to reach the top, we call this delta D top. So it's a positive value because the displacement vector pointed up. So let's now rewrite this. Notice that we can cancel out the negative on both sides of the equation. So 18 squared. We can divide both sides by 2 times 9.8 in order to isolate for delta D top. And this gives us approximately 16.53 meters once we plug it into our equation. Once we plug it into our calculators. Now recall, they were actually asking us to find the maximum height. So the height from the ground to the hand and from the hand to the maximum height, which is why we had this capital letter H. This means we have 32 meters plus 16.53 meters. This is going to be 48.53 meters, which we can round it to approximately 49 meters. So the maximum height from the ground is going to be 49 meters. Now for part D, they're asking us to explain why we couldn't use half the time to answer A, half the time of A to answer C. So this whole path that I drew in white, that was our time interval, delta t. But because there's no symmetry, we couldn't cut it in half. The only time we can do half the time is, let's say that it landed from the same height that it was thrown. Then we can take advantage of the symmetry of the parabola. Which we could cut in half. But in this case, if we were to divide it in half, notice that there's a portion missing. So there's this entire portion of the parabola missing. So we can only apply this for symmetry. In this case, it wasn't symmetrical. That's why we can only use half the time to answer this particular question.